So any object undergoing simple harmonic motion, such as this mass on our spring, doesn't only have a displacement as a function of time, which is what we've managed to discover so far, but it's also going to have a velocity and an acceleration. So in this video, we're going to examine these. Okay, so we've shown how our displacement here can be represented by a phasor, and it rotates around the origin of an Argand diagram. And so we have it a e to the I omega t plus phi. But with any physics problem like this, we don't just interested in the displacement, we also want to know the velocity. And so the velocity of the object is going to be dx by dt. And so this, now, we have to differentiate this. Well, this isn't hard to do. We're differentiating an exponential. This, of course, is just a constant, so it doesn't differentiate. So we're just going to have an I omega factor come down from our exponential, and we're left with the same function as we had before. So we've got I omega a e to the I omega t plus phi with brackets. Okay, so this looks a little funny though, because it looks now we've almost got an imaginary velocity, which of course is again wrong. We must have a real velocity because we're talking about a physical system. But we need to remember that this complex exponential is, of course, or imaginary exponential is, of course, not an entirely a real number. And so when we multiply this imaginary number by this complex number, we're still going to have a real component left. And that's what we want because, of course, again, we've missed out this implicit real operator that goes at the front here. However, if we want to look at the relationship between the displacement and the velocity, what we really want to do is we want to write this as a phasor. And so what we want to do is we want to write I in the form of e to the I something. Well, I is just e to the I pi over 2, because if you remember, this is going to be cosine of pi over 2 plus I sine pi over 2. Well, cosine of pi over 2 is equal to 0, and the sine of pi over 2 is equal to 1, right? So I we can just rewrite as this times omega a e to the I omega t plus phi. And so this is just going to be equal to omega times a times e to the I, and now we've got omega t plus phi plus pi over 2. And so we have an amplitude, if you like, for the velocity. So the amplitude for the velocity is omega times the actual displacement amplitude. And then we have a phasor, but this is going to give us a phase difference compared to the displacement. Because the displacement doesn't have this extra pi over 2. So let's look and see what that gives us if we plot this on an Argand diagram. And so this is what we now have. So the blue line here shows the displacement. So we have the initial position of the blue line here is at phi, and then over time it gets this additional angle here, omega times t, and the velocity is always going to be at 90 degrees to it, and it leads the displacement, right? So it's ahead of the displacement, and this velocity too will rotate with a time, right? So both the velocity and the displacement will rotate together, and the velocity will always lead the displacement by an angle of 90 degrees. So what we have, if we go back to our velocity as a function of time, is we have this is equal to I omega a times e to the I omega t plus phi, where now I've taken away this constant phase and I've turned it back into I. So remember, we're taking the real part. Right, there's this implicit real operator. So let's expand this out. Well, we have I omega a times cosine of omega t plus phi plus I sine omega t plus phi. And so when we multiply through by I here, this part is going to be imaginary, and this part is going to be real. And so what we have for the velocity here is minus omega a sine omega t plus phi. And so this is our velocity if we want to write it out in the trig form. Now, of course, we could have got there a lot faster, because we could have just used a for our displacement. We could have just said x is a cos omega t plus phi, and then we could have just differentiated that, where we get a times minus omega sine omega t plus phi, right? Because cosine goes to minus sine, and we've got an omega in here, so we have to bring the omega out when we're differentiating with respect to t. So we could have got to this a lot more rapidly if we'd have just differentiated the trig function. But again, this is just to show you that it doesn't matter which route you take, whether you take the real part and deal with trig functions, or the complex way and deal with these imaginary exponentials, both times you will get to the same answer. And if you draw this on this phasor diagram, you will get a displacement line and a velocity line that has a different modulus, right, as shown here, different modulus, and leads the displacement by 90 degrees, or pi over 2 radians. Now, when it comes to velocity, it's not so easy to project this out into one dimension so that you can see it using shadows like we could for the displacement, because again, right, what we're interested in is we're only interested in the real component. So the velocity that we actually are interested in is just this projection onto the real axis. This is the real component of our velocity phasor. So to do that instead, what we do is we plot it on a 2D plot, where we have the time here on the x-axis as convention, and then up here we've got the displacement and the velocity showing. And for the sake of this, to make things simple, what we've assumed is that phi is equal to 0, and we're going to take omega equal to 1. And so what that means is that omega times a, and a equal to 1, so that omega times a is equal to 1. So that will give both the displacement and the velocity the same maximum value. So what you can see here is that the displacement follows a cosine curve, right? Because cosine of 0 is equal to 1, and so we have it here at 1, whereas the velocity curve follows a minus sine curve, because the sine of 0 is 0, but then the sine of pi over 2, so here the sine of pi over 2 is equal to 1, and so therefore it has to be minus sine of pi over 2, which is equal to minus 1. And so you can see here that you're getting a cosine curve for the displacement and a negative sine curve for the velocity, and so they both take the same shape, but there is a phase difference between them, and that phase difference here, of course, is just pi over 2, as we can see on the phasor diagram. Okay, so let's go back to our velocity. So we have v of t is equal to I omega a e to the I omega t plus phi. And the next logical thing I'm going to calculate when we're dealing with kinematics is, of course, the acceleration. And the acceleration is just dv by dt. And so I want to differentiate this one more time. So that's going to give me another I omega from this imaginary exponential here. And so what I'm going to end up with is minus omega squared times a e to the I omega t plus phi. So now I'm going to want to express this minus 1 in terms of e to the I something. So what I want is cosine of something plus I sine of something, and I want this sine to be equal to 0. So what's equal to 0? Well, I could have the sine of 0, and that would give me, I could put 0 in here, but that would give me 0 here. But here I want this to be equal to minus 1, and the cosine of 0 is plus 1. So what I want to put in here is pi, because the cosine of pi is -1 and the sine of pi is 0. So this is just equal to e to the I pi. So if I write out my acceleration now, this is omega squared times a e to the I omega t plus phi plus pi. And so what this tells me is that now the acceleration has a phase difference of pi with respect to the displacement. So in other words, it's actually what we call completely out of phase. It has exactly the opposite phase to the displacement. And we'll see that in the next slide. So if we go here now this has been simplified by saying that omega is equal to a is equal to 1, right? So what that means is that the displacement, the velocity, and the acceleration will all have the same amplitude because the displacement has amplitude a, the velocity has amplitude omega a, and the acceleration has amplitude omega squared a. And so if omega and a are both 1, all of these three quantities are the same. Now, of course, in general, that's not going to be the case, and these are going to have wildly different values. And we've also simplified it by making the initial phase equal to 0. Otherwise, we have too many lines on this diagram. And so this diagram is showing you the phase difference between all three kinematic quantities. This is the displacement, has an argument of omega t. 90 degrees ahead of the displacement, there is the velocity here shown in green, and then 90 degrees ahead of the velocity, there is the acceleration. Now again, of course, what we're interested in is the real part of the acceleration, and that's just this component here projected onto the x-axis, which is the real axis. So this shows us the phasors for all three kinematic quantities, and you can see that here that the displacement is always going to be exactly opposite to the acceleration, which is of course what we already knew, because if we draw this thing with the spring here, right, and this is our equilibrium position, the displacement here is x, and the force pulling it back is k times x, and this of course by Newton's second law is proportional to the acceleration. So the acceleration is always going to be opposite to the displacement, and that's exactly what we see here on this diagram. So it's good that we can do a cross-check and tie it back to the original physical system and make sure that this is something that makes sense. Now, if we want a value for the acceleration, well, we've got, in terms of the real quantities, we have now, it's minus omega squared a e to the I omega t plus phi, and we can write this out in terms of our trig functions. So it's minus omega squared a times cos omega t plus phi plus I, sine dot dot dot. This, of course, is going to be neglected because we only want the real part, right? Remember, we're taking the real part. So we're multiplying it by a real number, so this I sine part doesn't matter, we can get rid of it. And so this is our acceleration here in terms of a trig function. Again, we could have got straight there from differentiating our original a cos omega t plus phi. When we differentiate it to get v of t, this will give us minus omega, from cosine goes to minus sine, and then we get an omega factor here, so that's minus a sine omega t plus phi, which is what we already had for the for the velocity. And then to go one step further, we differentiate again. Well, sine goes to cosine, and there's no negative sign involved, so this is omega t plus phi, but because of the omega we get this extra omega here, so we get minus omega squared times a, and this gives us the acceleration, which again we can get at by just differentiating the original real expression for the displacement. And so now we've calculated all three kinematic quantities, displacement, velocity, and acceleration, for a simple harmonic oscillator. We've seen that they've got different amplitudes, but they all oscillate, and that we've seen that there's a phase difference between them, as we can see here on this phasor diagram. So the last thing to do is actually look how that phasor diagram projects into one dimension, and to do that we look at a plot here. And so what we've got is we've got time on the x-axis, and when we have the displacement, velocity, and acceleration all up here on the y-axis. And again, omega is equal to a is equal to 1, and phi is equal to 0, so these things all have exactly the same amplitude. Now previously we looked at the displacement, which is here in blue, and we looked at the velocity, which is here in green, and so now we have the acceleration shown here in red. And if you look at the blue displacement and the red acceleration curves, you can see that these are perfectly out of phase. The acceleration reaches a maximum when the displacement reaches a minimum, and vice versa. The displacement here is a maximum here, just when the acceleration is a minimum, and that they also cross the axes together, but going in opposite directions. So you can see that the acceleration is perfectly out of phase with the displacement, but just like the displacement and the velocity, it oscillates backwards and forwards. So we've just seen how both the velocity and the acceleration can be represented by phases just like the displacement, but that there is a phase difference between these different phases. So if we look at this mass spring system, we can see this clearly demonstrated here. When the mass is at the bottom, we have the largest negative displacement. If we take positive as upwards, then we have the largest negative displacement at the bottom. But we also have the largest extension of the spring, and so therefore the largest upwards going force on the mass, and that means we have the largest upwards going acceleration. So clearly the displacement and the acceleration are exactly out of phase with one another, because the largest negative displacement corresponds with the largest positive acceleration. Now if we look at the velocity, we can see that at the bottom, when we have the largest negative displacement or the largest positive acceleration, we have a zero instantaneous velocity. And if we go to the middle, where at the equilibrium position, the forces on the mass are exactly balanced, so we have zero acceleration. We're at the equilibrium position where we measure the displacement from, and so we have zero displacement, but we have the maximum velocity. So the phase shift between the velocity and either the acceleration or the displacement is going to be pi over 2. Now, the other thing we can see looking at this mass as it oscillates up and down is that the energy in the system is also changing form. At the bottom here, we have the largest spring extension, and so therefore we have the largest amount of elastic potential energy, but we have zero kinetic energy. If we get to the middle here, then we have a large velocity, so we have a large kinetic energy. We've got less elastic potential, and we've got a slight increase in gravitational potential. So in this system, we've got three types of energy that are all sloshing around from one type to the other. So let's have a look at that in detail, but we'll look at a slightly simpler system, which is our horizontal mass spring system, so that we don't have to worry about gravitational potential energy. Now, there's going to be two types of energy in this system. We're going to have potential energy, and that potential energy is going to come from stretching the spring. And we're going to have kinetic energy, and of course that kinetic energy comes from the motion of the mass, or the velocity of the mass. So how do we calculate these quantities? Well, if we look at the elastic potential energy of a spring that is stretched, it's a half kx squared. Now, we know what this displacement x is, right? We know that x as a function of time is equal to a e to the I omega t plus phi. So our potential energy, and we'll call that u then, should be a half k and then a squared e to the 2I omega t plus phi. So anybody who thought that that's correct has forgotten one of the things that we talked about earlier. This is not correct, right? This expression here is wrong because we've forgotten the real operator. Now, if we look at this, what this is going to tell us is that the energy oscillates and becomes positive and negative, and so we have negative potential energy. Well, you can't have negative potential energy unless you have an imaginary extension to the spring, so this isn't going to get us anywhere, and the reason is because we forgot to take this real operator. So this is just one of those lessons where, to show you that you have to be careful. When we're taking this x squared, you've got to be very careful what you're doing. So rather than use this, which is dangerous, what we're going to use is the real expression, a cos omega t plus phi. And so this is one of the few occasions where you really are better off using the real expression and putting in the trig functions. So what this means is that our potential energy is going to be a half k a squared times cos squared omega t plus phi. Now this is good because a cosine function that's squared will go between 0 and 1. Right? It oscillates like that. And so we are not going to have negative quantities for the potential energy, and so at least it passes that sanity check that the potential energy is always going to be positive. So this gives us the potential energy, and what it also shows us is that the potential energy oscillates. It oscillates with this cosine squared function between 0 and a half Ka squared, which of course makes sense because at the maximum displacement you have your amplitude is A, and so your displacement is A, and so the energy in the spring is going to be a half Ka squared, and since that's the maximum displacement, that's going to be the maximum energy stored in the spring. So that gives us the potential energy. Next, we need to look at the kinetic energy. Okay, so we've seen potential energy. What about kinetic energy? Well, our kinetic energy, call it T, is equal to a half mv squared. Now v, having learnt the lesson using our displacement, I'll use the real form, the trig form of velocity. So this is minus omega a sine omega t plus phi. So putting that into here, and we're going to get the kinetic energy is equal to a half m, and now omega squared a squared sine squared omega t plus phi. So if we look at this just to make sure it makes some sense, and we plot the kinetic energy versus time, what we'll see, let's assume we're starting with phi of 0, is we'll end up with something like this, which oscillates between 0, and I'm not a very good artist, but oscillates between 0 and some maximum value that'll be a half m omega squared a squared. And that's because, so this is 0 here, that's because we've got a sine squared function, so it'll never drop below 0, and that's good because we can't have a negative kinetic energy, because you can't have a, it's velocity squared, and the velocity is real, so you always have a positive kinetic energy. So that's good. It passes the sort of the rudimentary checks that we can do on it. Okay, so the next thing we want is we wanted to look at conservation of energy. Now, conservation of energy is a very important concept, so we'd better expect that the energy of our oscillator is conserved. But as you see, we've got this kinetic energy that's oscillating between some value and 0, and we've got a potential energy that's oscillating between some value and 0. So what we want to show is that the total energy of the system, E, which is equal to the kinetic plus the potential, and that has got to be equal to a constant because we've got no forces doing any work on this system. It's a frictionless surface, a perfect ideal spring that obeys Hooke's law, nothing else is doing any work, and so we'd better get a constant value for the energy, otherwise we've violated conservation of energy, and we're going to have lots of problems with physics because this comes about from a fundamental symmetry of the universe, that the laws of physics are invariant under translations in time. So in other words, it doesn't matter when I do an experiment, I will always get exactly the same results. So let's look at the total energy. Well, our kinetic energy we've already got is a half m omega squared a squared sine squared omega t plus phi, and then we add to that our potential energy, and that was a half, Ka squared cos squared omega t plus phi. So looking at it, this doesn't look too good. We've got a sine squared and a cos squared term, and so adding these together, sine squared, remember that sine squared plus cos squared is equal to 1, so that might be a way around it, but then in order for that to work, we'd need this to be equal to this. So is that the case? Well, let's have a look. If we look at the half m omega squared times a squared, we need to remember that omega here is our angular frequency, and it was equal to the square root of m over k. So this is equal to a half m, and now omega squared is k over m times a squared. So the m's cancel, and this is equal to a half ka squared. So our total energy now is a half ka squared sine squared omega t plus phi plus a half ka squared cos squared omega t plus phi. And so sine squared plus cos squared is, since we can take this half ka squared out, this is just equal to a half ka squared times sine squared plus cos squared, which is just 1. So our total energy is a half ka squared. And that, of course, is equal to the potential energy at the maximum extension of the spring, which is exactly what we'd expect, because when you get to the maximum extension of the spring, then you have no motion. The object is instantaneously at rest, so it has no kinetic energy, and all the energy of the mass is in the potential energy of the spring. And so this is equal to the total energy of the system. And so it works. We've got conservation of energy, but what we have is we have this oscillation of energy between the kinetic and the potential energy. So to show you what that looks like, we can look at this plot here. And so what this is showing you is this is the potential energy, so this is U, and this is the kinetic energy, so this is T, and it's showing you that the potential energy, assuming here we've got a phase phi is equal to 0, and we've got omega set to 2 radians per second. So we have at 0 time, we have maximum displacement, and the maximum displacement corresponds to all the energy being potential energy stored in the spring. The spring then contracts and drags the mass back towards the equilibrium position, and it accelerates, and so the potential energy is converted into kinetic energy, and eventually what happens is you get back to the equilibrium position. So this is now at equilibrium, but of course you're moving, so at this point you've got no potential energy because you've got no extension of the spring, but you've got all your energy in kinetic energy. This is where you're moving at the highest velocity. And then as you go out the other side, what happens is you start to slow down, and of course you're slowing down because you're stretching the spring, and so your energy is converting back into potential energy, and so here you are at maximum extension. Right, because you're at rest, you've got no kinetic energy, right? And then again, you go back to the center, and so here you are at the equilibrium position again, and then here you're at maximum extension, and so on and so forth. So it's not just the velocity and the acceleration and the displacement which oscillate backwards and forwards. The energy oscillates backwards and forwards between two types. So here we're oscillating between potential energy and kinetic energy, and again, this is a general feature for all simple harmonic oscillators. They oscillate energy between potential and kinetic and back again, or two other forms of energy. And so again, this is something that also oscillates in an oscillator, but it's important to remember that the total energy is constant. And so the total sum of the potential and the kinetic energy, no matter where you are in the cycle, always remains at a fixed constant value in accordance with conservation of energy. So we've now seen how the energy in a simple harmonic oscillator changes between potential energy and kinetic energy, such that the total energy of a system like this remains constant as required by the principle of conservation of energy. This system, of course, is a little bit more complicated because we've got two types of potential energy: the elastic potential energy in the spring, and the gravitational potential energy as the mass moves up and down in the Earth's gravitational field. In general, for a mechanical oscillator, if you sum all the potential energies and compare it to the kinetic energy, it will behave in that out-of-phase fashion that we saw for our horizontal mass spring system. So we've now dealt with the mass spring system, but now it's time to have a look at a slightly different type of mechanical oscillator, and that is the pendulum. And so that's what we'll look at in the next video.